Well, hello there. I'm Pete Luday, the chairman of the Immersive Digital Experiences Alliance, or IDEA for short. In this video, we'd like to share with you a recent demonstration that we put together to show the progress we've been making on the ITMF, that's the Immersive Technology Media Format, and in specifically, streaming immersive content across an orchestrated edge network. You'll learn about that as we go through this. I should mention in my capacity as chair, I'm representing Cable Labs, and in my day job, I'm a consultant for Mission Rock Digital, studying advanced media technologies and display devices based in San Francisco.
Let me give you just 1 minute about what IDEA is and why we exist. Our dream is that in the future, someday, not tomorrow, there will be something that's akin to the holodeck, where we'll be able to have an immersive, very wide display that allows you to be indistinguishable images from real life. And we think that the physics are possible, but challenging, and we need time to get there, which is why we started now. Our vision is that there would be a practical suite of interchange specifications, and that these would be display agnostic, so they're not dependent on any given display technology. Of course, we would want 6DoF sound to be a critical feature within the media format. And we also want to be in tune that the practical bandwidth needs for able to use commercial networks. So this is something we want to make sure that is compatible with commercial networks. And we want to be able to leverage the emerging media-aware networks. Networks have been underutilized, we believe, in terms of their capacity to manage content, and we want to rectify that shortfall. That all comes to what we call the Immersive Technology Media Format, or ITMF. And this is a format that you could stream or do a file transfer and support everything from a full holographic Lightfield display to multiplanar or multifocal point, VR, traditional stereoscopic 3D, and even 2D displays. They would be downsampled, and that would be accomplished through a media-aware network, and also having display-specific renderers. On the high-end dense light fields, we believe that it's really not practical to bring all of the individual pixel information or subpixel, and therefore it would be reconstructed at a renderer. We put this alliance together almost 3 years ago to develop a family of royalty-free technical specifications, very importantly, to gather marketplace and technical requirements. So we're very in tune with what's going on in the display community and also the content creation community. We want to be able to facilitate interoperability testing and demonstration and produce educational events a couple times a year. We've been doing seminars and workshops, and to provide a forum for exchange of information. We have some of the most experienced network operators and light field experts as part of our team, bringing computational photography, display and network architecture skills into the group. And we're always looking at other people that might be interested. You can learn more by going to immersivaalliance.org. We have a mailing list that you could easily join. And you could also download the ITMF specification. It's open source and free. There's a suite of specifications you'll be learning more about today. And speaking of today, we're going to be featuring our network architect from Charter Communications, Del Wolfensparger, who will be doing much of the demonstration for us. We'll have presentations from Thomas Alder from Otoy, and also Austin Paul from Cable Labs, both the software engineers. And to start out, we're going to hear a little bit about the motivation from DJ Lyle, the Senior Director of Emerging Technologies for Charter Communications. DJ, take it away.
Thanks, Pete. So I'm DJ Lal, Senior Director at Charter Communications for Emerging Technology, Advanced R&D, and Ecosystem Development. I chair the Network Architecture Workgroup at IDEA. In this workgroup, we actually look at these experiences, these new digital experiences, and try to explore that balance that exists between compute latency and bandwidth to kind of understand what those future operating points could be for adoption of these experiences at scale. So we all understand, speaking of compute, we all understand that graphics-based experiences are extremely compute intensive. Today, a lot of that is because of rendering, shading, level of detail, lighting, physics, etc., etc. And we all know that, in order to deliver the best, most photorealistic experiences, you need high-end GPUs. But these are very expensive to acquire. Not everybody has desktops that have $2,000 cards in them, right? So this basically drives our belief system, which is that some or all of this must be leveraged from the cloud, right? And speaking of latency, I'd want to point out that latency requirements, unforgiving latency requirements, can be driven either by that motion to photon latency that is well documented with headsets, VR, AR, and such. And then it can also be driven by interactivity. A good example of that would be a large number of people working on a single 3D asset and trying to manipulate it in real time, right? And similarly, bandwidth, we know that today, even a single VR stream goes upwards of 50 megabits per second, can be 100 megabits per second, sometimes even higher, depending on what that quality is of or resolution is. And this is for today's headsets. And you can imagine that with the increasing resolution or resolution moving in the direction of retina grade, this bandwidth requirement is only going to go up. So in summary, the Idea Network Architecture Work Group is trying to understand how these experiences can be delivered at scale, how they can be democratized. And with that, I will hand off to Thomas, who will talk about ITMF.
Sweet. Thanks, DJ, for your overview of the Network Architecture Working Group. I'm excited to share what we've been hard at work on this past few months at a joint meeting. But first, let's get a better understanding of what exactly ITMF is. So the Immersive Technologies Media Format is an open source, royalty-free specification aimed for the end-to-end support of immersive media content creation, packaging, and network transmission. ITMF itself is based on the Orbix file format that's been developed by Otoy in collaboration with Mozilla and Autodesk. So it was released in 2014, and Orbix has been used as an interoperable format in Octane Render and its plugins across 20 plus industry digital content creation tools, some of which are available in a free tier for Blender, Daz 3D, Unity, and Unreal Engine, for example. Octane and Orbix is based and extended from the Academy Award-winning book PBRT, designed for photorealistic, physically based rendered scenes. And it's a standard file format used across the decentralized rendering network Render and the end format of the Otoy light stage captures. The ITMF specification suite is available on IDEA's website, as Pete mentioned, and is composed of 3 parts. It's binary container package, the XML scene graph defining the render node graph system, and data encoding specification designating the scene graph's code points for encoding and decoding. The container itself is a binary random accessible package utilizing the binary markup language to encapsulate the scene graph, any associated metadata, and all assets within a simple virtual disk system. Its structure is flexible, supports different encoding structures designed for interoperability and streaming, and it has compression and encryption capabilities for the packaged data and binary encodings. The scene graph provides an XML representation, providing a feature set to describe a complete, physically accurate, synthetic 3D scene based on the PBR node system from Octane. The node graph itself is very verbose. It has numerous node categories that cover many different aspects of the scene graph. And this diagram only contains a subset of all the possible nodes, but these categories include things like geometry, volumes, textures, material, light sources, cameras, and animations. And all nodes feed into what's known as a render target, and that defines the final rendering settings and final output. Elements of the scene graph are constituted by many industry-proven formats, and they all specialize in the portions of the scene graph that they cover. So ITMF umbrellas these formats as subformats, such as OBJ, Alembic, FBX for geometry, OpenVDB for volumes, OpenEXR for textures, as well as output for composition, and then support for other developing industry standards such as universal scene description, Arnold standard surface and volume, Material X, and OpenColor IO will soon be supported within the render graph. And any functionality of these subformats is naturally inherited by ITMF. The format also allows extensibility through the usage of scripted nodes in both Lua and the open shading language. So this extensibility, along with nodes that are defined for things like pattern generation, volumetric gliding, these provide procedural-driven mechanisms for textures, materials, and geometry. And these procedural scene elements can drastically reduce these file sizes by providing compute mechanisms rather than data. So within future capabilities of MPEG-I this week in the breakout groups, we've been discussing the usage of ITMF within the architecture for the distribution of immersive media, targeting immersive displays, and ideas continue improving ITMF while maintaining backwards compatibility to Orbix to include things like live action capture and hybrid techniques, audio, support for emerging volumetric formats, and interfaces to a heterogeneous array of applications and displays that will provide the means for an immersive experience. So with that, I'd like to turn it over to Del Wolfenswager, XR architect at Charter, who will present a live demonstration of our implementation of 3D streaming using a source ITMF file.
Thank you, Thomas, for that introduction. It's a very exciting time in Immersive, and I'd like to share this presentation with you because I think it's an excellent demonstration of a possible future where we could stream 3D to holographic devices. So let's begin. So what you're going to see today is based on an architecture, which you're going to hear about in more detail later from Austin Paul from Cable Labs. I'm going to give a brief overview here. What you're essentially going to see is the ITMF file after it's been decoded and encoded and placed on an edge server. Once it's on the edge server, we need to send it to the client over the network. In this case, the client is the Unreal Engine, and that is the intermediary between the Looking Glass Factory portrait display, which is our final display, which we will show the content on. So holographic streaming presents a number of challenges. The most important one being that it's a multi-U device. And one of the reasons we use the Unreal Engine is because a lot of the multi-view is handled by the plugins from the manufacturers of the displays themselves. And that's what's happening today. We're actually using the portrait displays plugin from Looking Glass Factory in order to talk directly to the display. However, when we stream the ITMF file, we turn it into something that Unreal can understand before we do the stream. We call this the encoding part of the process. Not too dissimilar from how you would encode an MP4 file if you were going to stream frame-based media. Using the GPU is mission critical for our architecture. And for real-time content, the GPU does an outstanding job in Unreal Engine, and that's why we used it. I mentioned before that we're using the Looking Glass portrait as the target, but we could also stream to VR headsets, Lightfield displays, basically any type of display or immersive device which is supported by Unreal. And last but not least, Unreal has a real-time rendering engine, much like Unity and the other game engines, and we find that that is mission critical to the delivery of 3D content. So let's talk a little bit about the Looking Glass portrait display. This has been recently launched by the Looking Glass Factory. It is a consumer-friendly holographic display because the price point is about $299 or $300. It's approximately 8 inches in width, in height, and the viewing cone is about 58 degrees. And what's unique about this display is that as you move from left to right, or whatever your viewpoint is, whoever is watching it, it can be multiple people, each view is from a different degree. And there's about a 58-degree viewing cone that you can view from. The resolution itself is 1536 by 2048, so roughly 2K. And the number of discrete views is between 45 and 100, depending upon how the developer has set up the content. A question that comes up to us as we were doing the development is why would you stream to Unreal, or any game engine for that matter? And essentially, all these standards are available to us through years of development by these game engines: OpenXR, ARKit, ARCore, Windows Mixed Reality. As you can see, Steam VR, for example, there's many different standards that are supported by Unreal Engine, and we are able to talk to all of them using our method. So, without further ado, let's begin the holographic streaming. I want to mention before we start that we are going to show the streaming in a sequential order, and in the future, we'll be streaming to a buffer, and then we'll be able to recreate 3D streaming just almost as you see it when you watch a 3D film, such as Frozen or Toy Story. Okay, here we go. This is the Octane render from Otoy, where we created the original scene. And this is an animated scene. You can see all the assets are already in. You can see the scene graph. And then from here, we take it right into our encoding, and we prep it for display. Now you're seeing it on Unreal. And now we're streaming directly to the Looking Glass portrait display. As I mentioned before, it is multi-view, so we're turning the camera left and right so you can see it. And momentarily, we'll be streaming the tire in. Should come any moment now. There we are. Next will be the road, followed by the animations. We have complete control over the 3D assets in the scene, which is one reason for doing this. We can control pre, post, and at the moment, in real time, all elements of the 3D scene, which means that we can create and destroy assets as needed. In this case, everything is coming into memory, which is very important to us, because when you start out, you're basically starting out with an empty application, and at the end, you've filled it up in memory with all the assets. And then at that point, all the assets are destroyed when the user quits. So in a sense, we've created something that has great potential for DRM and protected content. And the foreground object just came in, which was the suspension bridge, and that concludes the first demonstration. So the second demonstration is going to be slightly different. We're going to be showing Unreal Engine rendering in the cloud on an edge network, and then we're going to be streaming directly to Unreal in a hybrid mode, so that we're streaming content onto a mesh, and it's going to be a video texture. And the target in this case is Windows 10. So why would you do this? Well, in many cases, the compute of the device is not strong enough to show a high resolution texture. And so we're trying to bridge that gap that exists between compute available and compute in the cloud. This gives us the freedom to render more complex scenes on mobile devices, and there's a big advantage to doing that. And we're about to find out why. Let's take a look behind the scenes. Layer 1, in this case, the bike, is rendered locally, as you can see. Layer 2 is we bring the 3D mesh in, and then the 3D mesh is streamed in as a video texture using H.264 or any other video codec which we decide will be best for the streaming, and also based on network constraints. If we have a slow network, we can make up for that with traditional methods that are used for buffering and optimization of video codecs. Once we have the two layers together, it will appear to the user as a seamless scene, and they should not notice any difference between the actual video texture that's been streamed to the mesh and the rest of the scene. So let's go take a look at what this looks like in person. Here we go. So here's the bike just streamed in. Now the tire, which has the video texture applied to the mesh. So take a good look at that. You're also getting a little bit behind the scenes look at how things look when our camera is pulled out a bit, so you can actually see the objects that have been streamed in. Foreground object, which was a suspension bridge. And here is the tire with the video texture applied. So that concludes the demonstration of the first and second part of 3D streaming to a holographic device. I'd like to say at this time that we've also done further research into what could be next in our roadmap. And we're looking at Unity, which also has similar properties to Unreal in terms of real-time rendering and streaming. So that's definitely a target on our roadmap. In addition, future Lightfield displays are on the horizon. Lightfield Labs just announced theirs, I believe, earlier in time here. And we expect to see more. The nice thing about this is we expect the game engines themselves will adopt support for those. So we intend to be somewhat prescient about future uses of 3D streaming to immersive displays. Now I'd like to give you a more detailed view of streaming architecture. And in order to do that, we have Austin Powell, who's an associate engineer at Cable Labs, who will give you a detailed explanation of how everything works behind the scenes.
Thanks so much, Del. Before I get started, I really want to give a shout out to Thomas and Del. The reason that we're here today is because of the countless hours of hard work that they put into this project. And we're a small team, but I really think that they accomplished a lot here. So I can't thank them enough for making this possible. Thanks, guys. So I'm going to talk about the architecture of the demo that you just saw, and then I'll get into some of the advantages that we see in this system. So essentially, what we're going to do is we're going to walk through a diagram that tries to break down each of the different steps in this process. And at the end, we'll have time for questions if you have any. So first, what we're looking at here is we have some ITMF file that we're hoping to stream over the network and ultimately render on these different types of output devices. So this can include things like immersive displays, like the looking glass portrait that Del just showcased, AR, VR devices. We also want to be able to support legacy 2D displays, and we also want to be ready for everything that's going to come in the future as best as we can. So essentially what we're doing here is we take this ITMF file and we upload it to something that we call the codec server. The codec server decodes the outermost layer of the ITMF file, the ITMF container, which Thomas talked about briefly earlier. And we're using a tool that I'm going to talk more about later called libITMF, which is open source and recently published by IDEA. And so that's going to extract the meshes and textures and things like that from the ITMF file. So once we've done that extraction, we take the assets, again, meshes, textures, animations, things like that. We put those onto a CDN, which sometimes you'll hear us call the asset server. These assets we want to make sure are available at low latency to the clients. And then what we do is we take the ITMF scene graph, which is, again, Thomas talked about this earlier. It's XML based,
and we parse that and we upload it to a MySQL database. So once we've done that, we have this notion of something we call a device profile. And this is essentially all of the core information that you need about the output display and what client hardware is available to be able to render the scene that we're working with. And so this device profile is submitted by the client to the codec server that gets parsed and also propagated to the MySQL database. Now we have this notion of something called the network orchestrator cluster. And a network orchestrator is essentially the brains of the streaming operation. When we start streaming to the client, this is going to be the main server that's communicating with the client. And so what happens is the network orchestrator retrieves something called, which we call the scene to device mapping, which is JSON formatted. Essentially, it's a merge of the device profile and that ITMF scene graph. We are trying to get a representation of this scene that has everything that we need to be able to render on this particular type of client with this particular type of display. So the network orchestrator cluster receives that mapping. We leverage a tool called RethinkDB in this demo to get low latency regional synchronization, because we want this to be distributed across different geolocations, and we want to be able to have this available to the client at the lowest latency we can get in our cluster. So when it's time to render, the closest network orchestrator will start sending real-time JSON scene information down to the client. These are just bits and pieces of that mapping that we built earlier. Kind of like you can think of like commands that are read by an Unreal plugin that we've built that's going to build that scene in real time. And as it's building that scene, it's going to receive information about meshes and textures and things like that that it needs access to. So the client is going to start sending requests to the CDN to receive those assets, which can then be streamed individually in whatever way is most efficient for those particular assets. Dell's example is very straightforward. A video texture we can stream using H.264 or H.265 as appropriate. So we see this as an important detail in the architecture because assets are so heterogeneous. We have so many different types and patterns within these different elements inside of the ITMF file that we want to stream them independently with whatever's most appropriate for that type of asset. So now the client has received the assets, it's received the scene information, it's built the scene, and now we can render to any of these different types of displays. And so that's the high level idea of the architecture that we're working with here. So now I want to touch briefly on libITMF. Again, that was on that codec server we're using it to unwrap the ITMF container. This is IDEA's first major open source release. It's a C++ encoder decoder for the ITMF container spec. It's open source at GitHub on this link. The development is ongoing. Thomas Alder and I have been the main operators on this project, and we're always welcome to taking contributors. So if anybody's interested, please let us know. So I just want to start talking about, at a high level, how this compares to traditional streaming. And what we're trying to say on this graph is we want to highlight one of the challenges associated with traditional streaming, which is that as the resolution of the devices that you're streaming to increases, so too do the bitrate requirements of a traditional video stream. In this case, we've computed some estimates for different types of displays based on the use of H.265. And what you can see is that as we move into these immersive displays like the looking glasses available today, we have to worry about orders of magnitude more data being transferred in order to be able to stream to that device. And we expect this trend to only increase exponentially over time as we get into displays like the Lightfield Labs display, which we anticipate to be full parallax in contrast to the looking glasses horizontal parallax. We're going to be having exponentially higher resolutions, and as a result, the bit rate is also going to be increasing significantly. So the reason that 3D streaming is a new paradigm compared to that is because each individual asset is only streamed when it's needed. And once it's been streamed down to the client, we don't need to retransmit those assets. We can reuse those as much as we want and as much as the hardware allows, storage space on the client disk or memory. We can reuse those assets as much as we want. So in this example, we've transmitted a motorcycle down from the CDN. It appears in a scene, and at some point it exits that scene. If it reappears later, as long as we've got space in the RAM on the client, then we can re-render that motorcycle without having to retransmit it from the CDN. So to give you an idea of where this can matter, we wanted to show this example. Let's say that we're transmitting or we're streaming 1 hour of content to the Looking Glass 8K. So with traditional video streaming, again, we're just estimating this based on H.265. An hour of content would end up being about 135 gigabytes on the Looking Glass 8K. On the other hand, with our 3D streaming approach, we only have to transfer the total scene size in terms of all the different assets that we're working with. And then that scene information is generally very small. It's just some basic metadata. So in our demo, our 3D scene was only 63 megabytes. So you can see there's a big order of magnitude a complexity difference that we're dealing with here when we switch to 3D streaming in this particular case. So now I want to talk briefly about split rendering. Del already talked about this, but just to reiterate, the idea with split rendering is that we have some CDN. Again, you might hear us call this the asset server, or we have some edge compute resources. That edge server is going to render the most resource demanding, high fidelity scene elements that we want to present. And then those can be streamed to the client using something like H.264 or 265. And then the client will render the remainder of the scene that was not rendered on the edge. And then we composite those in some way. In the demo, we rendered those edge elements as a texture embedded in the scene. We've also seen some prior work in split rendering where they did some compositing, like you can see in this example with this apple here. So it's a really powerful method. And essentially what I'd like to highlight about the benefits are you are able to present higher fidelity content in real time than would normally be practical on lower end or consumer grade client hardware. And I see this as an interesting opportunity. With split rendering, you can essentially mix 3D streaming, like our approach, with traditional video streaming, according to whatever hardware and network constraints that you're dealing with, so that you can get the best quality possible under those constraints. So I think there's some room for future work there, kind of exploring how to find the sweet spot between 3D streaming and traditional streaming dynamically to really get the best performance out of your system. So with that said, I'm going to pass it back to DJ to wrap up the talk, and then we'll move on to Q&A.
Yes, thank you, Austin, and thanks for giving me that great segue there. So just focusing back on the big picture here, here's a little 2x2, an expression of what we're trying to do. So on the x-axis, you have the client or the display compute. And on the y-axis, you have bandwidth. And so what we see with traditional flat encoding, the kind of encoding we're used to on rectangles, is that, if you keep using it, this pixel-based construct for ever and ever, essentially it's going to lead to more and more compute as well as more and more bandwidth, pushing us essentially in this 2x2 in a region of high bandwidth as well as high client compute. ITMF streaming gives us an opportunity to think about this a little different and convert some of that pixel-based streaming into a more scene graph-based streaming, which, those logical constructs allow us to reduce the bandwidth, albeit not necessarily the client compute, because with ITMF, the client actually has to do some render, right? And so that's why ITMF streaming is kind of shown in the bottom right, where the compute is still high, but the bandwidth has gone down significantly, right? And then by mixing some of these concepts of split rendering and edge computing, what we can do is kind of achieve the right balance where we can hopefully push back the requirement on the client or the display compute by essentially supplementing it from the network, and thereafter start operating in a region of low bandwidth as well as low client compute. And I think with that, I just encourage everybody to engage through MPEG or directly with ITMF. And we encourage participation. And on to questions now.
Hey, thanks very much, DJ. And also thanks to Austin and to Dell and to Thomas for all that good information. I know we've crammed in a lot. We have a few minutes left for questions, and I'd say get right to it. Before I forget, first of all, you could type your questions into the Q&A box. We'll try to get to all we can. You can contact us through immersivEalliance.org for more information. And of course, we'll be making these slides available through MPEG or on our website. I can't tell you the exact logistics. The first question that came in is, are 3D assets streamed in RAW or compressed format? Who wants to take that?
I can take that one. So yeah, we stream them in using whatever compression is appropriate for that particular type of asset. So we're in the middle of researching different options for example, mesh compression. We are interested in Draco and some other formats as well, but that's also something that we're in the middle of developing.
Very good. Thank you. Next question was, in the split rendering circumstance, is there a communication path back to the server from the client to inform about the potential changes of the camera orientation and the position?
Yeah, I can take that.
Oh, go ahead, DJ.
Yeah, so I mean, with holographic displays, given that it's not a stereoscopic display where your head pose is essentially triggering a pose information, let's say, back to the server, this actually may not even be a requirement, because with a holographic display, you're actually using a relatively large pipe and you're delivering multi-view representations all together at the display, such that when different people view that display, they're all getting perspective accurate view of the hologram, right? So that path back, at least as implemented, may not be required. It may be required only for interactivity reasons on the content. Del, would you like to add something to that?
No, I think that's a pretty good answer. I would only add that, one of the nice things about what we're doing is that there can be two-way client to server communication, so that not only in the question that was asked, but also, we can make changes to the 3D assets at the client even after they've been delivered. So, for instance, we can change the blue wheel to a red wheel, or the bike to a gold color instead of a white color. So there are some very interesting dynamics that we haven't quite implemented yet, but we're on the verge of doing so.
And Austin, did you have some comments on that as well?
No, I think Dell summarized it quite nicely. We're interested in that interactive use case as a potential future, as a hopeful addition as soon as we can get to it. So.
Another good question come in. It says, thanks for the nice looking glass display demo. With the announcement of the Lightfield Labs solid light display last week, when could we expect to see the ITMF demo for such a dense immersive display? I'll remind everybody that the Lightfield Labs was one of the founding members of IDEA. So, of course, the crew there has been intimately involved in providing guidance to our ITMF development. And in terms of the time frame, I think that we can't really be talking on behalf of any of our members. Lightfield Labs does have a marketing program and introductions, and I'm sure they'll be giving you all the latest information on the website. I think it's safe to say, though, when Lightfield Labs is ready to do further public demonstrations of their technology, that certainly as a founding member of IDEA, that the ITMF solution will certainly be a component in what they're going to be talking about. We still have time for any other questions here, but I think the one thing that I've heard come up before is about split rendering. And is this something that we see implemented in networks over the next few years, or what might be the rollout for when we could start to take advantages of the benefits of split rendering?
Well, I work for Charter Communications, and so we're very concerned about the network and delivering content from the edge. So I can't make any predictions on that in terms of time frame. I'll just say that I work with DJ Lal, and that's in a conversation that we have several times a month as to what does that implementation look like. And we've done a series of tests to explore that.
Good, and I think it's been very. Go ahead, DJ.
Yeah, in summary, all I say is resources are not finite, whether it's compute, bandwidth, or latency. Network resources or cloud resources, they're all finite in nature. So we have, been working on this concept called the Network-Aware Media Protocol, which really allows us to explore split rendering and do it for holographic displays.
It's been very exciting, I must say, as part of IDEA to be considering all these other factors, because I think that the ecosystem of future media distribution is going to be much more than just a compression scheme or an encoding scheme. So we're benefiting from having very strong feedback from the display manufacturers who are giving us practical input into what displays are actually going to need across a multitude of technologies. Secondly, from content producers that are informing us as to the type of requirements that they need, the preservation of fidelity, latency, things like that, maybe things that are not so important. And then the network, as you've been hearing, it's very good to be able to hear all three of those, what the network providers are able to bring to the party, what the content producers need, and what the display manufacturers require in order to achieve this.
Well, with that, we're out of time, but thanks very much for joining us today. I hope you learned something. You can learn more about the IDEA, or contact us, or subscribe to our mailing list, or download the ITMF standard, or even join the Immersive Digital Experiences Alliance by going to our website, immersivealliance.org. Thank you.